Hi all. So in this video, I'll be discussing about the quantum coherence function, particularly the first order coherence function. So we have already discussed that the direction of light is depending upon the photoelectric effect usually. Okay, that means whenever the light incidents on the detector absorbs it and produces a photocurrent. So in that way, detection of a light is basically a destructive process. Okay, so detection of light is through absorbing photons and hence it is destructive. Destructive in the sense that after the detection, the light would be missing. That is a problem here. Okay. Now, quantum mechanically, we have seen that the electric field can be represented as an operator. So that thing we have discussed in the third semester while we are discussing the atom field interaction or the quantum mechanical theory of the atom field interaction. We have represented the electric field operator. So quantum mechanically, electric field operator can be written as E RT would be equal to I times square root of H cross omega by 2 epsilon 0 V. Okay, so that should be sum over K. So I sum over K square root of H cross omega K to epsilon 0 V, where V is the volume in which the field is confined. AK e raised to I K dot R minus omega T minus AK dagger e raised to minus I K dot R minus omega kt. Okay, so this can be divided into two parts. In the positive frequency part, we can write E plus RT, which contains the annihilation operator, and another one you can call it the negative frequency part. We can write E minus RT, which contains creation operator. Okay, so E plus contains annihilation. Okay, now we already discussed that the photo detection is a destructive process. So therefore, only annihilation operator may be contributing for detection of photons. So hence, the transition probability of a detector for absorbing a photon would be proportional to the annihilation operator. The transition probability of the detector for absorbing a photon. So we can write maybe P1 RT. So that would be proportional to the inner product F E plus RT I mod square. So where I and F are the initial and final state of the field. So I and F are initial and final states. Okay. Now the initial states is not known to us, and as well as the final state also not known to us. But finally, there may be many possible states. So therefore, the total probability should be sum over all possible final states. So hence we can write this P1 of RT would be sum over F mod square of F E plus RT I square. So this would be equal to sum over F E plus RT I and I. Okay, so this complex conjugate become E minus RT F. So just rearrange it. We can write this term first, and so it become I E minus RT. The summation can be taken to the inside. F E plus RT I, and hence using completeness relation, this would be equal to the identity operator. So finally, it become I E minus RT E plus RT I. Again, as we said that the initial state is again is not known to us. So therefore, the total probability, this might not be the correct expression, because the state I and need not be a pure state. Okay, the initial state need not be a pure state. In general, it will be a mixed state. And mixed state usually represented by symbol the density operator. So the density operator rho can be as sum over I Pi I. So the mixed. So this is a usual representation of the mixed state. It will be represented by the density operator. So the initial state, there are many possibilities, and the corresponding probability for a particular state I is Pi. So density operator, we can write the sum over I Pi, the outer product II. And hence, in terms of the density operator formalism, what would be the expectation? What would be the total probability? So the total probability P1 RT. Usually we write it's a trace of rho and E minus RT A plus RT. Now this probability is called the first order coherence function, or the first order quantum coherence function, or quantum correlation function, denoted by symbol G1 RT. So G1 RT, the trace of rho E minus RT E plus RT. Now the trace would be sum over some other symbol. You can use sum over J inner bracket J rho E minus RT A plus RT J. And what is rho? It's equal to sum over J sum over I Pi outer product II, E minus of RT, E plus of RT, J. So now this inner product Ji is delta Ij. Okay, so Ji would be orthonormal. So it becomes sum over Ij Pi delta Ij inner product I E minus of RT E plus of RT J. So better sum it over J. So if you sum it over J, just replace all J with I. So if you sum it over J, then sum over I would be remaining. It become Pi inner product I E minus RT E plus RTI. So this is what is called the first order quantum coherence function. Okay. Now, so we can have the most general expression for first order coherence function. G1 of R1 T1 R2 T2. This would be the trace of rho E minus R1 T1 E plus R2 T2, or is sum over I Pi the inner product I E minus R1 T1 E plus R2 T2I. So now we can define the normalized first order quantum coherence function. Is denoted by symbol G1 R1 T1 R2 T2. That is the quantum coherence function capital G R1 T1 R2 T2 divided by square root of G1 R1 T1 G1 R2 T2. Okay. Now, depending upon the magnitude of this normalized quantum coherence function, we can classify the coherence into three categories. So if the magnitude of G1 equal to 1, we get complete coherence. So we have similar result compared to the classical. And if the magnitude of this normalized first order quantum coherence function is between 0 to 1, we have partial coherence. And if this G1 is 0, then we have complete incoherence. And this complete coherence, we can connect this complete coherence to the factorization as well. So if we can factorize this, the average of E minus E plus can be factorized into the average of E minus into average of E plus, then we'll get the complete coherence. So the factorization is also the condition for factorization is also a condition for the complete coherence. Okay, so whenever if you can divide this E minus into E plus equal to E minus into E plus, we get complete coherence. Now E minus is depending upon A and E plus is depending upon A dagger. Or if you want, we can express that in terms of the creation and annihilation operator as well. Okay, so for the time being, it is not required for us. We are just concentrating our definition and its consequences. So for the first order coherence is basically measures the coherence of the light at one particular point at two different time. So it gives the measure of coherence time, and as well as from coherence time we can get the coherence length. So it is only the correlation of field at one particular point at two different times. Okay, so that's all for now. So the classical coherence function, the classical first order coherence, and quantum mechanical first order coherence we already discussed with this the last two videos. The next video we'll be discussing about the higher order coherence, and it's basically motivated by one experiment done by uh, the Hanbury Brown and Twiss. Okay, so that is the experiment which performed in early 1950s. So that experiment motivated the definition of the higher order coherence. So we'll be discussing about the classical second order coherence and quantum mechanical second order coherence in the next video. Okay, so see you then.